Hello everyone, my name is Harini and I'm a PhD student at Monash University, Australia. Thank you for the opportunity to present at the ICGE Colombo 2020. My presentation today is on the use of a novel graphene-based geotextile under hydro-thermo-mechanical loading in pavement applications. I would like to acknowledge the research team of my project, which is a part of Spark Hub, Smart Pavements Hub Australia. My supervisors, Professor Bouazza and Professor Kodikara from Monash University, and my industry partner, Geofabrics Australasia. To give a brief introduction, various pavement distresses, including cracking, rutting, wear, and deflection, are important indicators of pavement performance. There are many factors that affect how the pavement behaves, such as traffic loading, climatic changes, and pavement materials, which in fact lead to these distresses. Therefore, it is important that we monitor these loads and temperatures to accurately predict pavement performance and also to make assumptions of rutting and fatigue phenomena. Currently, pavement monitoring depends mostly on in-situ measurement techniques. These allow real-time monitoring of the road health condition in terms of stress, strain, deflection, temperature, and moisture content by integrating sensors within the road. However, most of the methods are intrusive, while they also can only provide information on discrete locations. Additionally, monitoring vehicle loading is also crucial for effective vehicle management and to prevent pavement overloading. For example, one overloaded heavy vehicle causes several times greater damage to the pavement structure than a properly loaded one. Therefore, vehicle volume surveys, mass and speed surveys are important. Inductive loops and wave motion systems are two of the most accepted technologies used by Australian road agencies for this purpose. However, the installation and maintenance of these systems are extremely strenuous. Therefore, it is understood that new techniques are needed that enable spatially continuous monitoring of pavements. Talking about geotextiles, in the scope of pavements, a typical road formation will have various components where geotextiles have applications in separation, reinforcement, drainage, and sealing. Also, nonwoven geotextiles are used in geotextile reinforced seals, or GRS, to reduce reflective cracking from underlying cracked pavements. Geotextile reinforced seals can be used to provide more robust waterproofing and as a SAM or SAMI treatment. Geofabrics Australasia, using the graphene technology of Imagine Intelligent Materials, has manufactured a graphene-based geotextile named Bidim C. This is a non-woven geotextile with the graphene coating on one side. Graphene is a highly conductive material, and the integration of graphene to the geotextile gives it promising conductive properties. It is used to test liners for defects via a closed electrical circuit forming at the leak location through the geotextile, and is currently used in waste, containment, and landfill applications. This invention provides a way to still keep the same purpose that the geotextile is designed for, with an added function of sensing, which enhances its benefit in any structure it is used in. So how can we potentially use this material in pavements? So if we take this picture here, several current paths exist between any 2 points on this graphene coating. And as an external stimulus is applied, the connections between the graphene fibers or the conductive parts are distorted, which manifests as a change in electrical resistance. So if the material is conductive, its electrical resistance can indicate how much deformation the material has undergone. And when these two variables are reliably related, they can be standardized for field applications. This builds the key research question of my project. Can the graphene-based geotextile provide spatially continuous information on pavement hydro-thermo-mechanical loading? To answer the previous research question, the project is arranged in achieving three main aims. The first is to characterize the electrical response of the geotextile under different loading conditions and to develop preliminary analytics. The second aim is to capture the response using an experimentally validated numerical model. And the final aim is to develop an appropriate field measurement technique. So moving on to the research carried out to this date, to characterize the material, tensile tests were conducted to obtain the relationship between the relative resistance change and strain. The resistance of the material was measured while the sample was being extended. The parameters for test standard wide width tensile test for geotextiles were used, and samples of both machine direction and cross machine direction were tested to find if there is any direction dependency in the electrical behavior. 4 specimen sizes were used to see the effect of size on the resistance variation, and the obtained data was fitted into a linear curve to calculate the slope, also known as the gauge factor for each specimen. This figure here shows the typical stress-strain relationship and the dr over r naught versus strain relationship obtained by the above tensile tests. So in the scope of this project, as it is aimed to deal with applications in road infrastructure, strains only up to 10% were used for further analysis. Here I have given some results I got only for 2 specimen sizes for 50 millimeter and 200 millimeter width for comparison. An average gauge factor was calculated for 5 repeated tests for each width per direction. It could be observed that larger the sample size, lesser the variability of the obtained resistance change results was. And the varying gauge factors along machine direction and the cross machine direction indicated an anisotropic behavior in the resistivity of the material. This figure here shows the standard deviation of the obtained resistance change results denoted by error bars. The error bars clearly demonstrate the different strain ranges within which the material can be used to measure strains with varying accuracy levels. Therefore, 3 such ranges were identified. So between 0 to 2% strain range, it can be used as a load sensor to measure strains in the asphalt layer and in weigh-in-motion systems. Similarly, from 2 to 5% strain range where the accuracy is not as high, it can be potentially used to measure cracking or high rutting. For the strain range of 5 to 10%, it can be used in early warning systems for sinkhole detection and slope failure monitoring. Therefore, it can be seen that the applications are vast for this material in road infrastructure and the versatility is proved. So to interpret the tensile test results in a macroscopic point of view, a constitutive approach is used by coupling Maxwell equations, which are updated with piezoresistive constitutive equations and structural mechanics equations as follows. The general Ohm's law is updated by the piezoresistive conditions to obtain the following updated Ohm's law for piezoresistive materials. And the piezoresistive equations relate the induced strain to the relative change in resistivity using the piezoresistive strain coefficient G. A computational model was initiated in COMSOL multiphysics platform, assuming the material to be homogeneous and the graphene coating to be uniform. And the anisotropy of resistivity was also accounted for in the G matrix. Linear elastic conditions were assumed for the mechanical model, and the model was calibrated using the experimental data to find G. Also, strain-dependent piezoresistive coefficients are to be found to capture the non-linearity in the electrical response of the material. So this is a snapshot of the overall research plan elaborated stage by stage. So this shows the research to be carried out, including the research aims that are planned to be achieved from the proposed research. With this, I have come to the end of my presentation. Thank you very much for listening.